All right, let's do some practice with some of the Snell's law and quantities affecting light when they change mediums, materials, and that type of stuff. So let's start with some basic stuff, no big deal, and see what we can do. So let's take some red light here. So we got some red light, and we'll just have it starting in some air, nice and simple, and then it is going to then go into some glass. So let's do some really basic stuff. And of course, as light goes from air to the glass, it's going to definitely get smaller. Okay, so let's see if we can find out a few things about the situation. Okay, now in air, red light, you're probably looking around on, well, higher end. The wavelength of red light in air would be about 700 nanometers, and it's going to go into glass. So let's find out what is the speed of light in the glass and what is the wavelength in the glass. Okay, so let's start with some basic stuff. So first things first, the speed of light in the glass. Speed of light in a material is equal to c divided by the index of glass. And if you remember from the previous video, we talked about glass. Glass has an index of about 1.5. There's variations of glass, but averages are around 1.5. Okay, so if we use that, 3 to the 8 is speed of light in a vacuum. Air is pretty much, it's very, very close to a vacuum. And if you look at the index for air, it'll be like 1.00. You have to go to a few more decimals to get something. But it's pretty much, we just use, for what we're doing, we can just use 3 to the 8. So we take 3 to the 8, speed of light in a vacuum, we divide it by the index for glass, which is 1.5. And we've had this before. It's going around 2 times 10 to the 8 meters per second in the glass. Okay, and then for the wavelength, we will do something very similar. Okay, so it's all about the index. If we want to find out how much things change, if we remember when we did this Snell's law derivation, there's all these ratios. There's ratios, ratios, ratios. It's all about ratios. And one of them was the wavelengths. We had wavelength of air or wavelength or glass would be index to the glass, index for the air. We had a wavelength index ratio. And it's really, it ends up working very similar to how the speed changes. If the index gets 2 times higher, the wavelength is going to get 2 times smaller. It's the same type of ratio. And we have our values that we can use for this. We have the wavelength in the air, that's 700 nanometers. The wavelength of glass that's what we're looking for. The index for the glass is 1.50. The index for air is 1 basically, which means we won't really do anything. And then we can solve for the wavelength in the glass. So all we do is like a little cross multiplying, no big deal, just a little crisscross, basic math from a while ago. And if you do that, you should get a wavelength about 4.67 times 10 to the negative 7 meters. Which would be like 467 nanometers. It's really common just to write wavelengths of light, especially visible light, in nanometers. So it's just a little cross multiplying. So it's actually not that difficult. It's all about ratios, setting up the ratios, and that's about it. Okay, so let's try something similar. All right, so let's start with glass this time. So we're going to start with glass. And I have a little piece of glass, so this is all nice piece of glass. And let's say we go into some water. So there's some water. All right. Instead of drawing wiggly stuff, we can also draw wave rays. We talked about using wave rays before. So we could draw some light coming in, some green light. It's going to go into the water. Okay. So inside the glass, we've got some green light, and then it's going to go into the water. No big deal. Now we know that the index for glass is 1.5. We have used that before. And in water, light is actually a little bit faster in water than it is in glass. In water, light will travel around 2.25 times 10 to the 8 meters per second, something like that. Okay, so let's say we have our green light. Green light in a vacuum, green light all by itself has got a wavelength around 520 or so, 525, somewhere around there. There's a bit of range, of course, and we can sort of figure out what is the wavelength of green light in here. And I'm going to tell you right now, the wavelength of green light in a vacuum is around 520 nanometers. Actually, I'll get rid of this little g right here because we might confuse the green with the glass. There we go. Okay, and we will find out what is the what is the index for the water. So there's two things we're going to find. So what is the wavelength in the glass and what is the index for water? Okay, well, let's start with the index for glass, or wavelength for glass. All right, so the wavelength for the glass will be the wavelength in a vacuum, which is 520, divided by the index for glass. So we're just going to take the 520 nanometers, we can divide that by 1.5. We know it should get smaller. It's never going to be bigger than it is in a vacuum. So we'll just divide the two out, and we will get approximately 347 nanometers for a wavelength of green light in glass. All right, so now let's try and find the index for water. Well, the index for water, we have the speed, so that makes things easier. We take the speed of light in a vacuum and we divide it by the speed of light in water, which is 2.25 to the 8, and you will typically get around 1.33 or so for an index of water. Okay, so glass is around 1.5, water is around 1.33, so they're actually relatively close-ish. Glass is a little bit more. Okay, so there's just some basic practice using some of the index ideas and wavelength ideas and that type of stuff. So now let's see if we can actually apply this to Snell's law and actually get some light to refract. Okay, let's start nice and simple. So suppose we have a barrier, something like this. There we go, and we'll do pretty standard type stuff. Well, let's just start with good old-fashioned air, and down here can be good old-fashioned water. And remember, the index for water is 1.33. We just did that. And air's 2 decimal places, just 1.00. No big deal. All right, so here comes the light. The light's coming in an angle, and it'll go in here into the water. If you remember, the angles are always measured from the normal. So there's a little perpendicular normal line, something like this, and that's where the angle is measured from. Now let's say we're coming in at 40 degrees, and I want to, what is the angle in the water going to be? I know it's going to be smaller. All right, well, this is where Snell's law kicks in. So according to Snell's law, N for the air, sine theta for the air is going to be N for the water, sine theta for the water. I know the index for air, I know the index for water, I have the angle for air. The only thing I don't have is this. So sine theta for the water is going to be the NA sine theta A divided by N water, and we can solve for that. Now the only thing is when you actually calculate this, it's going to give you sine theta. So you have to inverse sine it to actually get the angle. Okay, so we'll punch those values in, inverse sine it, and get the angle in the water. We know it has to be less than 40. Okay, so it's going into the material of the higher index, and you just see it, like the angle there is going to be smaller than 40. All right, so we punched out. Don't forget to inverse sine it, and we get an angle of around 29 degrees. So this angle in here would be 29 degrees. Okay, basic Snell's law. All right, let's try another one with the other two materials we were using. Okay, we had some glass before. Okay, so here's some nice glass. Okay, and here's some water. We dealt with water before, good old-fashioned water, something like that. We know the indexes for these. Glass is about 1.5. Water is around 1.33, something like that. And let's bring in some light. Maybe we have some light coming in like this, and then bending off this way. Okay, and let's see what we can do. And let's say it came in over here. Let's say it came in at 15 degrees, and I want to know what is the angle in the water going to be. Now, water has a lower index, so I know the angle should get bigger, so it has to be more than 15 degrees. So similar to up here, okay, sine theta W is going to be the index of the glass times sine theta for the glass divided by the index for the water, And again, you're going to punch all that out. Don't forget to inverse sine it, and you will have the angle in the water. And if we punch all that out, get around 17 degrees. So not a huge difference because the indexes are relatively close, but there we go. Okay, all right, let's try something else with this. Do that. Okay, so let's try something else. There's your little, draw a little boundary here again. All right, there we go. And let's just start with some glass again. Good old glass. All right, so no glass is 1.5. All right, so we got some light coming in to glass, something like this, and it refracts something like this. And let's say over here came in at a 50-degree angle, and then refracted inside of here, and let's say it's only 20 degrees in there. And I don't know what that second material is, but I want to know what is the index for the second material and how fast is light in that second material. Okay, well, I can use Snell's law to find the index. Okay, so N2 would be equal to N1, or the index of the glass, times sine theta for the glass, divided by sine theta 2, and I know what the two angles are, and I know what the index for glass is, so I can find the index for the second material. I know the index is going to be higher than 1.5 because the angle's smaller. The bigger the index, the tighter it gets to the normal. Okay, so I'll punch this out and get that second index. So let's see, if I do that, I get index of 3.36. Really common to put indexes to 2 decimal places. Okay, well now that I have the index for that material, I can figure out other stuff. I can figure out how fast it's going. So speed of light in the second material would be the speed of light in a vacuum divided by its index. So I've got the 3 to the power of 8, and I just divide that by the 3.36 that I just found. And I can find out how fast light is actually going in there. And it's only going around 8.9. Okay, so it seems like really big, but the decimal's different, times 10 to the 7 meters per second, so something like that. Okay, so that's the speed of light in that second material using refraction. Okay, so that's kind of how this works. And we can even incorporate other stuff in there as well, but that's the basic application of Snell's law and using the properties of refraction to solve for different things.